Hello. Purpose of today's video is to look at solving trigonometric equations where the equations are not directly sinusoidal. For example, here we have cosine squared instead of just a regular cosine, or we might have other things happening as you'll see in the further examples. Anyway, as you may have experienced in working with math so far, when we have an unknown inside a function, our first goal is to strip away all the things that are being done to the function before we can invert and get rid of the cosine itself in this case. So I need to divide by 9 and then take the square root of both sides so that I can find just the cosine of theta equals. Then I have to do the next stage, which is finding the value of theta. So first to solve for cosine and then to solve for theta. Divide by 9, take the square root of both sides. Caveat here, remember that positive and negative numbers squared both yield a positive result, so we have to consider both possibilities. Then we end up with two conclusions. Theta is either the arc cosine of 2/3 or the arc cosine of negative 2/3. Now, your book and me, which seldom agree, but in this case we agree, we should be looking at how to interpret this graphically for two reasons. Number one, we see we have to go from 0 to 360, and we should know that our calculator does not give us arc cosines or arc anything that goes up to 360 degrees. So we're going to get more angles than what our calculator is going to tell us. So the graph is really helpful because of the symmetry of the graph. We can say, look, if the calculator is going to give me this angle here, then I just have to subtract that same number from 360 and I'll get my second angle here. Similarly, if the calculator gives me my first angle here, then I'll use symmetry and get my second angle by taking 360 minus that angle. So calculators give us 48 degrees and 131 degrees respectively. So I can find the other two angles by subtracting from 360, and therefore I have a list of all four solutions. Now, of course, what I should do is verify this, and one of the ways to verify would be to take any one of these angles, take the cosine of that angle, square that cosine, multiply by 9, and then see that you get 4 as a result, which is kind of fun. Another way, which makes more sense to do this in the first place, but our job is to learn about thinking and reasoning and math skills, not to get answers. But if I needed a quick answer and I wasn't concerned about theory, then all I would do is graph y equals 9 cosine squared of theta, make sure that I'm in degree mode, and I type in y equals 4, here's the red line for y equals 4, and then 1, 2, 3, 4 solutions. Here I found the third one, which is 228.18, which is one of my 4 solutions. I wouldn't be surprised if finding the other 3 be the same. So, similar vein, we have a trigonometric equation here, and this one is another one of those reminders that we do not divide variable expressions to eliminate variable expressions, because in so doing we will lose solutions. So the algebraic approach for solving this is to use factoring. Before I do that, I thought I would demonstrate that if I did not use factoring, but if instead I used canceling, as students often call it, if I tried canceling this stuff out, I would find only one solution, in my own estimation, from negative pi to pi for the arcsine of 3/4. But when I graph the given equations and find their points of intersection, I find actually 5 solutions. 5, I didn't even see that coming. So we have to be really, really careful about our work, especially eliminating variables through division. We want to avoid that altogether. So the best way to do this is to bring everything to the same side of the equation and then use factoring. So here I factor out a sine from both sides, and then I use the zero product principle, which enables me to find values of theta, the arcsine of 3/4 and the arcsine of 0. And for the arcsine of 0, I could do that in my head, 0 pi and negative pi. And for the arcsine of 3/4, I would get 0.848 and 2.294. Those are radian values, of course. So I can list all 5 solutions accordingly. Now the last one I would like to look at, oh, and by the way, of course, I checked it all with technology, so we're good to go. Last one I want to talk about is a little bit of a difference in philosophy from the way the book illustrates how to do work with this trig and the way I'm used to doing it. Now in the given situation, particularly what I'm looking at is sine waves and cosine waves, or tangents, where the period has been changed from its original. Because what that's going to do is it's going to, in this case, compress the sine wave, so we're going to see 3 sine waves in the normal space that we used to see just 1. We're going from 0 to pi, but where do we stop giving answers based on the fact that the period has changed? So I'll show you how your book authors designate to do this. And they say start by solving for x, just like you always would. So first we get rid of the sign. But what we have to do when we get rid of the sign, in order to find the arc sine of negative 0.02 within the appropriate range, and this is the thing that I understand, but it's hard to explain. If we want to find how many of the sine waves we need, or sine angles that we need to be able to find that make this true, we need to actually account for the stretching and shifting of the original sine wave. And an efficient way to do this would be to take your restrictions of inequalities and force x to become 3x minus 1. In so doing, we multiply both sides by 3, so now we have 0 between 3x or 3x between 0 and 3 pi, and then we're going to subtract 1 from all three sides and get this statement. So I'm going to look for all the arc sines of negative 0.2 that fall not within 0 and pi, but within negative 1 and 3 pi minus 1. And this again accounts for the compression and the shifting of the original sine wave. So when I go through here and do this, I can see 3 different solutions. So I actually then will take 3x minus 1 and set it equal to each of my 3 values and find my 3 solutions accordingly. Only one that directly comes from the calculator, sadly. So that's again, this little technique right here is a way to, if you are solving or if you're using the arc sine in an equation where the sine has been transformed by stretching horizontally or compressing horizontally, then modify your domain restrictions in order to determine which pieces of the arc sine you want to keep. Now again, frankly, I do not condone this method. I think there's a more direct approach that's a little safer too, but it requires really good graphing skills. In this case, I would suggest graphing y equals the sine of 3x minus 1. And then when you put in a horizontal line for negative 2, you will only have to look between 0 and pi. You only have to look between the given restriction set anyway. So here's what I would do. First of all, my observation, this is a really, really quick graph, and all I was trying to do was to show what the sine of 3x would look like. So here is 2 pi. Oh, sorry, I don't even know what I'm doing anymore. Yeah, by the time I got to 2 pi, I would see 3 whole sine waves, or in other words, 2 pi over 3 represents 1 period. So here's 2 pi over 3 right here. I got 1 sine wave, and then I got another half a sine wave left. So that's within my domain restriction, but the only thing I have to do now is to take that graph and shift it all over to the right 1. And so doing, I had to re-extend my graph backwards. But once again, if I can correctly graph this thing so that it's shifted properly, I can see 1, 2, 3 solutions, and I can even predict where they're supposed to be and what they're in between. So then when I do all the algebra, I should get the same 3 numbers, and it's easier to confirm using technology that those are the 3 correct solutions. So thanks for watching. I hope this was helpful. Have a good day.